on this question, we are going to graph the equation y equals 3x squared by plotting points. So I've got a chart here for x's and y's and then ordered pairs. And this equation is written as y equals 3x squared. So it's going to be easier for me to choose values of x and find the values of y so that I can have ordered pairs. So I'm going to choose just my standard set of x's, -2, -1, 0, 1, and 2. And let's find the y to be 3x squared. That's 3 times -2 squared. And we need to make sure that when we simplify this, we follow order of operations. We need to apply the exponent before we multiply. So -2 squared is 4, and 3 times 4 is 12. So this gives us the ordered pair -2, 12. Continuing on to the next x value of -1, that would give 3 times -1 squared equals 3 times 1. -1 squared is 1, and 3 times 1 is 3. So we have the ordered pair -1, 3. For the next x, we have 3 times 0 squared. That's 3 times 0, which is 0. So we have the ordered pair 0, 0. 3 times 1 squared. That's 3 times 1, which is 3. We have 1, 3. 3 times 2 squared. That's 3 times 4, which is 12. So we have the ordered pair 2, 12. So now that I have a few ordered pairs, I'm going to put these ordered pairs on the graph, and I hope a pattern shows up. -2, 12, -1, 3, 0, 0, 1, 3, and 2, 12. So you can see this U-shaped pattern emerging. We connect those points with that U-shaped pattern. This is called a parabola. And we have now sketched the graph of the equation y equals 3x squared by plotting points. For this question, we want to find the x and y intercepts of the graph of the given equation. That's 2x minus 7y equals 4. So when we're looking for an x-intercept, what we do is we substitute in a 0 for y. Now the reason why we do that is because if we're thinking of the graph, I'm just going to make up a graph here. Let's say it's a graph like this. An x-intercept is going to be a point where the graph crosses or touches the x-axis. All of those ordered pairs will have a y-coordinate of 0. And so if we choose y to be 0, we're going to be able to solve for the x that we don't know. So we're going to substitute a 0 in for y, to get the equation 2x minus 7 times 0 equals 4. 7 times 0 is 0, so we have 2x minus 0 equals 4. 2x minus 0 is 2x. I'll divide both sides by 2 and get x equals 2. So the ordered pair 2, 0 would be the x-intercept for this equation. We also want to find any y-intercepts. So to find the y-intercept, we're going to substitute an x for 0, a 0 for x. So if we're thinking of our graph and looking for a y-intercept, we're going to be focusing on where the graph crosses the y-axis, and that ordered pair has the x-coordinate being 0, which is why we substitute a 0 in for x. So in our equation, we'll substitute a 0 in for x, giving us 2 times 0 minus 7y equals 4. 2 times 0 is 0. 0 minus 7y is negative 7y. And we'll get y by itself by dividing by negative 7 on both sides. That gives y equals negative 4 over 7. If we're going to write that as an ordered pair, that would be 0, comma, negative 4 over 7 for the y-intercept. On this question, I want to find the equation of the line passing through the points 4, 2, negative 4, 8. I want to write the equation in point-slope form, slope-intercept form, and standard form. So when I'm trying to find the equation of a line, I'm typically going to start off using point-slope form. In point-slope form is y minus y1 equals m times x minus x1. So in order for us to use point-slope form, I need to know an ordered pair, that's the x1, y1, and I also need to know the slope of the line. Now with the information I was given 2 ordered pairs, so I can use either one of those ordered pairs as the x1, y1 in the formula, but I don't have the slope. But I am able to calculate the slope using the slope formula, y2 minus y1 over x2 minus x1. So let's calculate the slope using these 2 ordered pairs. I'm going to let one of the points be x1, y1, and the other point be x2, y2, and substitute into that formula for slope. So y2 is 8. We'll do 8 minus 2 in the numerator. x2 is negative 2, so negative 2 minus 4 in the denominator. 8 minus 2 is 6. Negative 2 minus 4 is negative 6, so I've got a slope of negative 1. So now that I have both the slope and a point on the line, I'm able to use this point-slope formula to find the equation. So I will use this ordered pair here in my point-slope form. That's y minus 2 equals negative 1 times x minus 4. So I have the equation written in point-slope form. I've done this part. Then I want to write the equation in slope-intercept form. Now slope-intercept form is y equals mx plus b. It's named that because we have the slope, and the b in this equation is the y-intercept. So I want to rewrite my equation, which is in point-slope form, into slope-intercept form. So to rewrite it in slope-intercept form, I'm going to go with a goal of writing it as y equals. So let's get rid of the parentheses using the distributive property. That's negative x plus 4. And then to get y by itself, I add 2 to both sides. So that gives y equals negative x plus 6. So now I have it written in slope-intercept form. Okay, so I've done that part. Then I also need to write the equation in standard form. The standard form is when you have both variables on the same side of the equation. So we write that as ax plus by equals c. So you have both variables on one side of the equation and the constant on the other side. So I will start with my slope-intercept form because it's usually a little simpler than point-slope form. So I'm starting with y equals negative x plus 6, and I want to write it so that the x and the y are on the same side. So I add x to both sides to get x plus y equals 6, and this is my standard form for the equation of the line that passes through 4, 2, and negative 6, 8. So that was my final task there. So we were able to find the equation of the line in these different formats for the point 4, 2, and negative 2, 8. For this example, we want to evaluate the function f of x equals x squared plus 2x minus 3 at the given values of the independent variable and simplify. We have f of negative 2, f of x plus 6, and f of negative x. So we'll start with part A. We want to evaluate f of negative 2. We want to replace the x's in our function with the value that's given to us of negative 2. That will be negative 2 squared plus 2 times negative 2 minus 3. Negative 2 squared is a positive 4. 2 times negative 2 is a minus 4. 4 minus 4 would be 0. And 0 minus 3 is negative 3. So we found that f of negative 2 is negative 3. So then we want to do part B, which is f of x plus 6. And this time, instead of a number inside of our parentheses, we have an expression, the expression x plus 6. But we follow the same pattern for how we evaluate. We're going to replace this x in our function with the expression x plus 6. So that would be x plus 6 squared plus 2 times x plus 6 minus 3. And I want to simplify x plus 6 squared. That would be x plus 6 times x plus 6. Here I can use the distributive property to get 2x plus 12 minus 3. I'm going to multiply the x plus 6 times x plus 6. That would give x squared plus 6x plus 6x plus 36 plus 2x. And I'll go ahead and combine the 12 and then minus 3. 12 minus 3 is plus 9. Then we have x squared, 6x plus 6x plus 2x would give us 14x. 36 plus 9 will give us 45. So we've evaluated f of x plus 6 to be x squared plus 14x plus 45. Okay, one part to go. We're going to do part C, which is f of negative x. So once again, instead of a number inside of our parentheses, we have an expression. But we're going to replace the x in our equation with that expression of negative x. We have negative x squared plus 2 times negative x minus 3. Negative x squared, that would be negative x times negative x. A positive 2 times a negative x would give a minus 2x. And I'm carrying down that minus 3. A negative times a negative is a positive. We have x squared minus 2x minus 3. So we found that f of negative x is x squared minus 2x minus 3. For this question, we have a picture of a graph, which is labeled with g of x, and we want to know for what value of x is g of x equal to negative 8. When we have g of x equal to negative 8, we have to remember that g of x is the same thing as y. This is telling us that we have a y of negative 8, and we want to know what x value. So we're going to look on our picture for a y value of negative 8. We have a y value of negative 8 here. So on our picture, the only y value with a negative 8 would be right here, and that's the ordered pair for negative 8. So we can see it's an x value of 4 with a y value of negative 8. So I know that x is equal to 4, g of 4 equals negative 8. Use the vertical line test to determine whether the graph is the graph of a function. We have this graph that kind of looks like an S. We want to decide whether this graph is the graph of a function using the vertical line test. So with the vertical line test, what you should do is all along the graph, you should draw vertical lines. And you want to pay attention to how many intersection points a vertical line has with the graph. So I just drew one vertical line here, and it has 3 intersection points. So when you have more than one intersection point, that is an indication that your graph is not a function. So when we have a function, every x should have exactly one y. So if we have more than one intersection point, we're having more than one y for an x. So that's how you use the vertical line test to determine if you have a function. Draw vertical lines, pay attention to the intersection points. If you have more than one intersection point, then the graph is not a function. A certain radioactive isotope is a byproduct of some nuclear reactors. During an explosion, a nuclear reactor experiences a massive leak of this radioactive isotope. Fortunately, the isotope has a very short half-life of 10 days. Estimate the percentage of the original amount of the isotope released by the explosion that remains 4 days after the explosion. So this radioactive isotope has a half-life of 10 days. So this is going to help us figure out the rate at which the isotope decays. We're going to use this formula here. A of t equals A naught e to the kt to solve the problem. And A naught is the initial amount. K is the decay rate. T is the time. And then A of t will be the amount that we have after some period of time. So as I mentioned a moment ago, Having a half-life of 10 days is going to allow us to figure out K, the decay rate. So if we have a half-life of 10 days, this tells us that the amount that we have after time will be half of the initial amount, half of the starting amount, for a time period of 10 days. We're going to use those two pieces of information to substitute into our exponential decay formula, and we'll be able to solve for that decay rate. So in this formula, A equals, I'll write it as A of t. A of t equals A naught e to the kt. So our amount, because we're dealing with half-life, will change to half of our original amount for a time of 10 days. So now we're able to solve this exponential equation. We'll start by isolating. We're going to isolate by dividing by A naught on both sides, and that gives 1/2 equals e to the 10k. Now we can solve this exponential equation in a few different ways, but I'm going to take the natural log of both sides. Natural log and e are inverses of each other, and so they cancel out. On the right-hand side, I'll have 10k equals natural log of 1/2. I'll divide both sides by 10, and k is equal to natural log of 1/2 over 10. So now that I know that K, the decay rate, I'm going to be able to answer this question. Estimate the percentage of the original amount that remains 4 days after the explosion. Estimate what remains 4 days after the explosion. So let me give myself some space here. And now I am going to update my formula now that I know K. It's A of t equals A naught e to the natural log of 1/2 over 10 times t. So I want to estimate the percentage remaining 4 days after the explosion. So I have a time of 4 days. So I'll substitute a 4 into my formula, and that will be A naught equals e to the natural log of 1/2 over 10 times 4. So this side is the amount after 4 days, and this is the original amount or initial amount. So if I simplify this part of it, this is going to give me the portion of the original amount, the portion or percentage of the original amount. So I'm going to put this in my calculator so that I can get the portion of the original amount that'll be remaining. Okay, I've got my calculator up now, so we're going to type that e to the natural log of 1/2 over 10 times 4. And I like to put the 4 in the front. It makes it so I don't have to use as many parentheses when I'm typing in the expression. So I'm going to type e to the 4 natural log of 1/2 closing parentheses for the log, then I'm going to divide by 10. So if I were to turn this into a percentage, I would have 0.76 if I round to 2 decimal places. So 0.76 is 76%. 0.76 or 76%. 76% of the original amount will be remaining after 4 days. Twist. On this example, we want to use the graph of y equals 2 to the x and transformations to sketch the exponential function f of x equals 1/2 to the x minus 1. We want to determine the domain and range, also determine the y-intercept, and find the equation of the horizontal asymptote. So before we get too far into this, we do need to know what the graph of the base function looks like, y equals 2 to the x. So let's start by finding 5 ordered pairs on that base function so we can get an idea of what the base function looks like. So we're going to start off with a table, and I'm going to choose just a standard set of x values, -2, -1, 0, 1, and 2. And I'm going to find the y values, y equals 2 to the x. So I'm going to start down here with some of the easier ones. 2 to the 1 would be 2. 2 squared would be 4. 2 to the 0 power is 1. 2 to the -1 power. When we have a negative in the exponent, we're going to do the reciprocal of the base. So that'll be 1/2. And then we have 2 to the -2. 2 to the -2 will be 1/2, but this time we're going to square it to get 1/4. So we have these set of ordered pairs, which is going to give us a sketch of the graph. We have -2 and 1/4, -1 and 1/2, and we have 0, 1, so there's 1, 1, 2, and 2, 4. So this gives me a sketch of what the graph looks like. It's an increasing graph. We also know that we have a horizontal asymptote, which is right on top of the x-axis. That's y equals 0. We have a y-intercept that occurs at 0, 1. So I'm mentioning those because these are things that we're going to be asked about later in our transformed graph. This has a domain of all real numbers, and it has a range going from 0 to infinity. And I did not include 0. I put a parenthesis on 0 because of that horizontal asymptote. So then we want to find the other graph, the graph of f of x. So that's f of x equals 1/2 to the x minus 1. And at first glance, I'm looking at this and I notice that my base graph has a base of 2. However, this function has a base of 1/2, which, like I said, at first glance, you say, oh, those are different. However, remember what we said over here, that when we have a negative in the exponent, we do the reciprocal of the base. So I'm going to rewrite this function so that it has this base of 2 that we're starting with. So this is going to be a 2 to the -1. 1/2 is the same thing as 2 to the -1. and we have 2 to the negative x minus 1. So now I can see that those bases are the same, and I can use transformations to figure out the new graph. The transformations that I see in this equation involve that negative symbol. That negative symbol is going to be a reflection, and it's going to be a reflection horizontally over the y-axis. And then we have this minus 1 here, and that minus 1 is a shift, and that shift is going to go vertically down 1. So we're going to take this graph that we started with, and we want to reflect it horizontally and shift it down 1 unit. So if we were to do that, reflecting it horizontally would mean that the graph looks like this. And how does that affect our ordered pairs? So if we reflect it horizontally, that means that the x's become opposite of each other. So these ordered pairs will then change. Originally we had negative 2 1/4. That would change to now positive 2 1/4. Positive 1 1/2. 0, 1, negative 1, 2, and 2, 4. So that's only with the horizontal reflection. Then on top of that, you want to do your shift down. So shifting all those points down, let's draw a new graph here. Shifting all those points down would mean that my horizontal asymptote has now shifted down. So now my horizontal asymptote is at y equals negative 1. And how does that affect those ordered pairs? If we shift them down 1, that's going to subtract 1 from all those ordered pairs. So now those ordered pairs become 2 and 1/4 minus 1, 1 and 1/2 minus 1, 0, 1 minus 1, negative 1 and 2 minus 1, 2 and 4 minus 1. So let's simplify that. So that would become 2, 1/4 minus 1 would be negative 3/4. 1, 1/2 minus 1 would be negative 1/2. And we have 0, 0, negative 1, 1. And I made a mistake here, I think. This should have had a negative on it. It's negative 2 and 3. So that's how those ordered pairs have been affected. You do the opposite sign on the x and subtract 1 from the y coordinates. We've already mentioned how the horizontal asymptote has changed. How has the domain and range changed? The domain is still all real numbers, but because our graph got shifted down, the range is now negative 1 to infinity. Final thing we want to do there is find the y-intercept. We do have the y-intercept right here already. It has an x-coordinate of 0, but you can also calculate the y-intercept. Remember, our function is f of x is equal to 1/2 to the x minus 1. So we would let x be 0. That's 1/2 to the 0. Minus 1, 1/2 to the 0 is 1. And 1 minus 1 is 0. So we get the ordered pair 0, 0 for the y-intercept. We want to classify the given function as polynomial, rational, or root, and then find the domain and write the domain in interval notation. So this function is f of x equals 2x to the fifth minus 5x. We want to decide whether it is a polynomial, a rational, or a root function. And it's sort of easier to do process of elimination here. If you know what a root function is, a root function will have a radical in the function, a variable underneath the radical. A rational function, you should have a variable somewhere in the denominator. And since we don't have a variable under a radical or a variable in the denominator, here we have a polynomial function. I guess I should be a little bit more clear. Sometimes rational functions will have a negative in the exponent, and sometimes rational functions will have a fraction in the exponent. So we also don't have a fraction, we don't have a negative in our exponent either. So we do have a polynomial function, and what we know about polynomial functions is that there are no restrictions. So this is something that we just memorized. No restrictions means that our domain is all real numbers. So that would be negative infinity to infinity in interval notation. Thank you for checking out my videos. Have a great day.